Hi, I'm trying to measure the weight of the Leaning Tower of Pisa. Not only that, in addition to that, I'm going to find the height of this tower as well. Wait, why am I doing these things? The things that I'm going to find are called physical quantities. There are a lot of physical quantities you meet in physics. In order to find the magnitude of a physical quantities, we use units. Simply, if you are ever asked to define a physical quantity, you can say that anything measurable in physics is called a physical quantity. In order to measure the magnitude of a physical quantity, we use units. The magnitude describes how big a physical quantity is. Right, as you can see, physical quantities and their units, we already know physical quantities is any physical property that can be quantified and can be measured using numbers. I have introduced so many examples already. Mass, uh, amount of substances, weight. You can suggest more if you want. A lot of physical quantities are involving with this. And as you already know, we use units to measure the magnitude of these physical quantities. But out of all the physical quantities, um, we select some or seven simply basic physical quantities as fundamental basic physical quantities. Simply, these physical quantities dominate all the other physical quantities. Uh, let's try to figure out what these physical quantities are. Very first basic physical quantity is mass. So there are seven. I'm going to introduce all seven here. And the standard international unit. This is very important. If you don't know what standard international unit system is, this is the standard method we use globally to represent the magnitude of physical quantities, or these are the SI units basically. So the very first one, the SI unit of the mass is kilograms. And then we have length is the second basic physical quantity. And in order to measure the length, the appropriate SI unit is meters. We use meters to measure the length of the standard unit is meters, that which is used to measure the length of a particular object. And then we meet the next important one, which is the third one is time. The standard unit is seconds. I'm going to use a different color to show the next four physical quantities. The fourth one is amount of substances. If you're wondering what amount of substances is, we rarely meet the amount of substances in physics, but you'll frequently meet this concept or amount of substances in chemistry. We use moles to measure this. So if you don't know what exactly this term is or how to pronounce this term, which is moles. And then we meet one of our friends. The next important term is current, electric current. And we use amperes to measure electric current. Simply amps, I already mentioned the name of that. Right. The 5 is down. Now, the fifth one is one of the popular ones, which is temperature. If you're from America, sometimes you might frequently use Fahrenheit to represent temperatures, to indicate temperatures. Globally, the industrial unit that people use is Celsius, but in terms of science, we use kelvins to measure temperature. So this is called the Kelvin temperature or absolute temperature. We'll introduce or we'll come across absolute temperature later on. Till then, wait patiently and learn these concepts really well. We'll meet these concepts later on. Right, and then last not least, we meet one of the important physical quantities, which is luminous intensity. But we rarely meet this guy in physics, in Edexcel advanced level physics, but in higher studies and even in unit 5 we are about to meet luminous intensity later on. I will remind again when you meet this term again, right? We use candela to measure luminous intensity, CD candela. Right, that's all about the 7 basic and fundamental physical quantities. Why these things are fundamental? That's important because all the other physical quantities, for example, force, you already know what the unit is. We use newtons to measure force. But is Newton a fundamental unit? Not at all. The reason is we can derive a particular unit for physics in terms of these one of or two or three of these physical quantities. So then we can't ever consider it as a basic or fundamental physical quantity anymore. Let me explain it more. Now let me consider a physical quantity like this. Let me consider area. Right, we already know the area of a quadrilateral. If you ever wish to measure, the area can be defined as length into breadth. You can say length times or a times b or whatever it is, and the length can be measured in meters and even the breadth can be measured in meters, so you end up getting meters squared. So can you see that now there's no specific unit for area, but still in terms of meters we can define this unit. And when it comes to volume, the volume is length into breadth into height. You can say a times b times h or something, and if you ever wish to get the unit, you will end up getting meter cubes or meter cubes. Right, what else? You can introduce any more. If this was a live class, you would have introduced more physical quantities like this, but I'll pick one of the next physical quantities, which is I can pick density. Is a very good example. The unit of density or density can be defined as mass per unit length, in the sense mass over volume, and we have already come to know the unit of volume, which is a meter cube, and the mass can be measured in kilograms. So we end up getting kg m minus 3. Isn't it nice? Like a cup of tea. Good. And what else? The next one is I can pick one more example, which is momentum. No, we are too early to go for momentum. Something else we can pick. I can pick velocity. Velocity is measured in meters per second. I'm pretty sure you must have heard this before. But if you ever want to derive this, it's displacement over time. Displacement over time. So displacement is measured in meters and time is measured in seconds. We end up getting meters per second. Good. Right. So what else? We have acceleration. I introduce few more in case you need to dive deep. Acceleration is the rate of change of velocity can be defined as acceleration. For simplicity, I simply describe this as velocity over time, but it's somewhat deeper than just this equation. It's change in velocity over time. But For simplicity, I just considered it as velocity over time. Right, so if you ever wish to find the unit of this one, it is ms minus 1 over s. So you end up getting ms, and there are now two minus terms in the sense ms minus 2. Right, meters per second squared. Right, now, yeah, let me describe the unit of force. You have been waiting for this, right, until this one pops up. Right, now here we have force. Okay, here we go. Now force is force can be defined according to Newton's second law. If you have ever gone over this concept, the force can be defined as mass into velocity. Sorry, my bad. Mass times acceleration, according to Newton's second law. Right, now we have mass, which is measured in kilograms, and we have just come to know that acceleration unit is ms minus 2. In case you need this unit, you can use this one, but I highly recommend you to use the other one in case they ask, only if they ask you to define the unit of force in terms of basic units. You can write that kg ms minus 1, sorry, minus 2 is the unit. Right, now there are three questions. I have already sent you this. You might have already downloaded this worksheet. It must be there with you. This is the tube that you have to refer to. So I want you to try this out. There are three questions. Right, if you don't really know what the impulse is, I define what the impulse is. Impulse can be defined as change in momentum. Impulse is equal to change in momentum. Change in momentum. Right, so now if you want to describe, or if you want to answer these questions, right, I'll give you just a minute to think and answer. So then I'm going to answer these questions. Right, now it's pretty obvious that we have just come to know that apart from a velocity, all the physical quantities, all the given physical quantities are what? They're derived, basic physical quantities. So the only right choice this time is velocity. Let's move on to the question number 2. So kg ms minus 1, yeah, kg for mass and ms minus 1 for velocity. You end up getting mass times velocity. You end up getting mass times velocity, which is momentum p. So this is the unit of momentum. That's clear. And this is very interesting. Most of the time when when I ask my classes, when I ask my kids to do in my classes, in my physical classes, I have seen how students struggle with this, right? So they can't figure out the change in momentum and difference between change in momentum and momentum sometimes, right? So let me explain it like that. So imagine your weight is not your weight. Let me consider your mass is just 50 kilograms 10 years ago, and imagine your new mass is 80 kilograms. But you have been eating a lot, so your weight has gained in 10 years. Your weight has gained by 30 kilograms. So now here when you write change, so you can write the change in mass is equal to 80 kilograms is the final mass minus 50 kilograms is the initial mass. So we end up getting 30, right? But magnitude or the value doesn't matter here. That's not my major concern here. My major concern is this unit, right, which is measured in kilograms. So we measure, so we can still see that it is very similar to the unit of mass. So the unit of mass is equal to the unit of change in mass. Similarly, if you really want to find and I specifically mentioned you that impulse is change in momentum. Change in momentum So uh, this must definitely be carrying the momentum's units. So unit of the momentum, also unit of the change in momentum must definitely be the momentum's units. So this is very important, right? That's it. Okay, now next important topic is, as I mentioned in my note, some derived units have their own units. Exactly like what? Force has its own unit, which is newtons, and similarly we have pressure. The unit of pressure is pascals. So but they are not specifically basic or fundamental units, but they have some special units. Exactly, because those are, it doesn't mean that those are not important. Those physical quantities are also important, but uh, there are few special physical quantities like that I'm going to introduce. They have their own unit, but if you really want to define, or if you really want to describe, you can write in terms of basic units as well, right? For example, let me consider, or let me pick uh, force. Forces, conventional unit is newtons is what we use, right? And in basic units, that is kg ms minus 2. We have already derived this, that's why I didn't derive it again. And we have pressure. The unit of pressure is pascals, right? It's a special unit. But if you really want to define pressure, we can write the pressure P is equal to force over surface area. So force, the unit of force in basic units, it's kg ms minus 2 over area is measured in meters per second, m squared. So we end up getting kg m minus 1 s minus 2. Wow, feels good. What else? I'm going to use green color to derive the next one, which is our next special guy is work or energy. Work or energy, you already know the unit, as you have met this in IGCSE already. So is it's joules we use, right? Joules is the corresponding unit, but uh, you also can say work is equal to force times distance traveled in the direction of force. Distance traveled in the direction of force. So it is kg ms minus 2 times meters, which is kg m squared is minus 2. Right, you can still write this in, you can write down these things with you, sorry, with me. Just write down these things with me if you want, guys. And we have one more example, which is power. Yeah, let's try to define power. The unit of power is watts. We have the specific unit, which is watts. And if we define the unit of power, is black color, as I haven't picked black color yet. So power can be defined as rate of change of energy or work. We'll come across these concepts later on. Don't worry, guys. If you don't know, don't worry about it. Uh, just for now, consider whatever I say, right? So then P is equal to, you can say, work over time, because it's rate of change of work or rate of change of power. In the sense, work is measured in we already know the unit of work, which is kg m squared s minus 2, as we just got to know this. Then time is measured in seconds, so we end up getting kg m squared s minus 3. You can write several units if you want later on, but so these are a few examples that you can copy down if you want. I'll leave you to write down these things if you want. Right, we have gone through some couple of important lessons. It's high time to learn what power prefixes are. In physics, you can't always rely or numbers sometimes, because some we encounter some bigger numbers, sometimes some very small numbers, decimals. It's very hard to deal with numbers like this. So instead of just directly writing these numbers, we sometimes introduce um, a power prefix in order for that number to be very intuitive. For example, uh, just imagine 100 meters. And now I'm going to ask you to imagine 1 millimeters. So these are powerful terms. The milli term, when you put milli in front of meters, it means something important. So this is how powerful these power prefixes are. Let's quickly walk through this lesson. The next important topic is power prefixes. Right. Imagine a huge number. For example, if you ever wish to measure the distance between the Andromeda galaxy, the center of the Andromeda galaxy, and the center of the Milky Way galaxy. So Milky Way galaxy is our home galaxy, and the Andromeda galaxy is our neighboring one. If you ever wish to measure the distance between these two, and imagine your teacher wants you to write this value in just in meters. Uh, Imagine you are not allowed to write anything in scientific notation. You are just asked to write this value in meters like this. Imagine how hard this is, guys. You'll be in deep trouble, because writing this value in numbers is a torture, because it's very hard. And as physicists, guys, we are busy people, and we have more stuff to do rather than just writing a number like this. So we use power prefixes. We get the help of power prefixes in order to get rid of these difficulties like this. For example, yeah, you can see some of the power prefixes I have already put in my metric system prefixes here. Right, we have a lot of power prefixes, but most of them are not in use. Practically, we don't use all of those power prefixes, guys. But I have put almost all the power prefix that you every prefix I have put already here in case you want, but we don't really want to know all the power prefixes here. Right, so then very first power prefixes, you can see a lot of power prefixes like that I have for 10 to the power 1. Right, how could you write? For example, let me explain. You can refer to this table later on, and you can pick all the power prefixes. I'm not going to introduce one by one. You are smart enough to recognize all the power prefixes I have already put here. Right, for example, I have for smaller numbers like centi. Centi represents 10 to the power minus 2. Another even smaller one is 10 to the power minus 3. Is represented by milli, simple m, and we have a weird letter like mu. This is called mu to represent micro, right? Which represents 10 to the power minus 6, so on. So, but let me do a few examples, because that matters the most. Rather than learning the theory, sometimes better to know how to apply the theory. So let me explain first of all. Let me pick this one, 6.2 kilojoules. Right, now I really want you to write the following in standard form. So I want you to write this in standard form, and standard means, so you have to get rid of this kilo term. You are not supposed to keep it with you anymore, keep it with this anymore. You just want to eliminate the kilo term, and you have to write this with joules. So it's now 6.2, and instead of kilo I can replace 10 to the power 3. That's the task, because we already know that a kilo represents this k term, kilo represents 10 to the power 3. So why can't we put it over here now and leave it with joules? Yeah, now this is okay, because this is a standard way, standard conventional method that we use to represent values. uh, that's the scientific order we use, so therefore you can leave the answer as it is, 6.2 times 10 to the power 3 joules. Right, so how about this one? 800 nanometers, and instead of nano we can replace 10 to the power minus 9 meters, and you can end up getting 8 times 10 to the power minus 7. Even if you want, you can further simplify this and end up getting the last decimal value, but we don't want to go to that further because unnecessary effort. Right. Okay, how about this one? 43 milliseconds. Right, it's your turn now. 43 milliseconds. You can take the turn and do it if you want, but I'll do it for you. 43, and milli represents 10 to the power minus 3 seconds, so you end up getting 4.2. You can use your calculator. You are totally free to use your calculator. Don't keep it away. Minus 2 seconds, like that. Right, let's go on. You can do that. The next one is, right, so I'm going to leave these things for you, because these examples you will be able to do, and in case you are unable to find out anything, you are totally free to ask for help via the email that we have already provided. Keep in touch. Right, now let me do a few more questions for better understanding. I think we have to do a few more questions as well. Here, write the following using an appropriate prefix and unit symbols. This time, your objective is to convert the given value in meters or whatever the unit is. You have to convert this value into a value with a relevant prefix. So you have to choose a relevant prefix and represent the value. That's what your objective is. So the first value is 10 millions. Okay, let me choose a proper pen. 10 billionth. Guys, there's a little difference between, not a little actually, there's a significant difference between billionth and billion. Billionth represents 10 to the power minus 9 meters. Now, 10 to the power minus 9 instead of 10 to the power minus 9, you can pick one of the relevant prefixes. So I think the best prefix is nano. It's pretty obvious. Then I choose nano, and instead of 10 to the power minus 9, I replace 10 to the power minus 9 with nano. So I end up getting 10 nanometers. That's it. Right. Easy peasy. Now look at the second one. Let's go with the second one. It's 125 or 1250. Oh no. Yeah. So this value 1256,000. That's a huge value. So if you really want to convert this value into a value with a prefix, right? You have to pick the relevant prefix this time. First of all, that is your objective. So because if you can't find out the relevant prefix, you will be in trouble. So I'm going to recommend you kilo, or else you can, as you wish, you can pick whatever you want as a prefix. So if you pick another prefix like mega or something else, still you will be able to convert it into the value with the relevant prefix using this method. So what I'm going to do is, if I want to write it with kilo, in the sense a kilojoule answer, if I really want to write, I divide this one by 10 to the power 3, as I already know the 10 to the power 3 represents kilo. So I end up getting 1256 kilojoules. That's it. Or else, if anyone wants, in case you want to represent this value in mega, 1256, just write the same value again, and 10 to the power 6 is the corresponding 10 to the power, which represents mega. Okay, now you end up getting 1.256 megajoules. That is it. Right, now, yeah, Oh, we have come across uh, a smaller number this time, a decimal number. Doesn't matter at all. If you ever encounter a decimal number like this, right, so you already know you can replace it with a proper prefix which is less than a 10 or minus powers or the prefixes which represent minus powers. So what should I pick this time? You can suggest me. If this was a physical class, you would have suggested me a proper one, but it doesn't matter at all. We can have a physical chat, so we can have a physical conversation, and physical chat is alive anytime. You are totally free. Feel free to text me or send me messages. I'm waiting to respond to you. Right. So you can imagine now, if you want to represent this answer in micro with micro units, you can divide this one by 10 to the power 6. So you end up getting 1, 2, 3, 5, 6, 12.6 micro. Oh, my bad. 10 to the power minus, sorry, minus 6. As this value should be minus this time. Relevant prefix should be, the value represented by the prefix should be put here, and that is 12.6 microhertz. Therefore, that's it. Right. So I think you'll be able to do the rest of these questions. I'm not going to interfere. In case you find any difficulty, just let me know. Right. I'll help you with those questions. But now my concern is, so there are some, so in my tute, you'll be able to find out from page number 14 to above, you will be able to find some complicated or not complicated, I don't like to use that term, but some relatively challenging questions you will be able to find. I'm going to help you with these questions, not all of those questions. With some of the questions I'm going to help you. My first choice is fifth one, because I have noticed some kids are having a very hard time with these sort of conversions sometimes, right? So I have noticed this in my teaching career, right? So I have been teaching for a long time now, almost 7 years, and I have, but even some smarter kids, I have seen that some very smart kids sometimes they struggle with these questions. So therefore, I am thinking of helping you with these sort of questions. Don't worry. Let's get started. Now imagine 1 meter cubes. Let's try to convert 1 meter cubes into centimeter cubes, and you can use this conversion anytime you want, right? So in order to find how big 1 meter cube is, I draw a cube like this, a cube, right? So the length of the cube is 1 meters, breadth of the cube is 1 meters, even the height is already here, 1 meters, right? So the volume of this cube is equal to 1 meters times 1 meters times 1 meters, in the sense 1 meter cube. That's fine. But I can represent this 1 meters in centimeters. In the sense, I can write this value in centimeters. 100 centimeters times 100 centimeters times 100 centimeters. So I'm about to get now 10 to the power 6 centimeter cubes. Right. The conversion is very simple now. My conversion is now, if you ever get any value in meter cubes and if you want to convert it into centimeter cubes, simply you can multiply this one by 10 to the power 6. You will end up getting a value in centimeter cube. On the other side, if you want to go to meter cube end from centimeter, imagine you got a value in centimeter cubes, right? You can divide this one by 10 to the power 6 to convert it into meter cubes. Right, let me do the last example they ask us to work work out. So now the last example given here is they want us to convert 100 or no 1000 centimeter cubes. 1000 centimeter cubes is expected to convert into meters cubes. So we already know the approach. If you ever get a value like this, I ask you to divide it by 10 to the power 6 to convert it into meter cubes. So I will end up getting 0.001 meter cubes. That is it. That is it. Right. Okay. Keep it aside. Right. Now my next problem is, I'll go with question number 8, as it is not that hard, but a bit strange. So I will do this question for you. Now, I want you to find the unit of this t. You don't imagine, sometimes you might not know what this t represents, or what the t is. Simply this t represents time. In advance, I will need to mention, and t simply represents time here. So let me check whether we end up getting a proper unit to represent seconds or time. Right. Now time is measured in seconds, we already know, and let's try to get a relevant unit. Right. Now imagine you don't know anything about t. It's something strange. It's just a stranger. You don't know anything about this guy. You are going to find the relevant unit. Right. So now t is equal to the 2 pi doesn't have a unit. You can represent, you can leave 1 to represent that it is unitless. And length is measured in meters, and g is the gravitational acceleration, which is measured in ms minus 2 square root. Can you see now, m to m you can cancel out, s squared and the root of this, you end up getting seconds. Super cool, because yes, this is a period and the period is a time, and seconds is the relevant and appropriate unit. Right. Let me do one more example question. Now look at this. Gravitational force on each planet. You will encounter this later on. Right. You will get this, and in unit 5 we have this lesson, the gravitational forces and gravitational forces between objects, planets. We will meet this lesson later on. So this equation will show up later on. So F is equal to gm over r squared, where g is the universal gravitational constant, right? And m represents a mass, and even simple m represents a mass, and r is the distance between these two planets, right? So now they expect you to find the unit of the universal gravitational constant, but there's a condition. You should never forget the condition: with basic units. That is the condition. So under this circumstance, what I'm going to do is, if you ever get a question like this, make sure you subject g, as that is what you are going to find. So bring all the stuff onto other side. F r squared over gm, oh my bad, g is what I'm trying to find. So m and m. And the force, don't be silly, don't be stupid to put newtons here, because that's not a basic unit. So relevant basic unit, we have already come to know, it is kg ms minus 2 is the relevant basic unit, times here the distance is measured in meters, and even now this is a mass which is measured in kilograms, and this is also a mass which is measured in kilograms, right? Okay, now you can cancel out this kg to kg, and we can further simplify this, and something intuitive can be found. Kg minus 1, that's a power, and m to the power 3 is to the power minus 2. That is it, right? You can take a note if you want. Right, now we have you have a few more example questions that you can try anytime you want. And if you got any question, or if you find any sort of doubt or any difficulty, the marking scheme is already been attached. You can go over the marking scheme and try to clarify the issue as much as you can. But if you still struggled, you are totally free to text me via the given chat box. Feel free to send me a message. I will get back to you as early as possible. That is the end of the first chapter. See you with the next brand new topic, which is vectors.